So, I intend to cover all these topics and more if there is time today. And let me review what we have covered so far. We discussed topological manifolds yesterday and curves on the topological manifold. So, imagine that you have this topological space M, sometimes I call it M, sometimes S, does not matter. We know that a topological manifold is a set endowed with a topology T, so that we have notions of open sets and all that. And then we saw that you can have open sets U1, U2 and so on. You cover the entire manifold with a collection of open sets, and then you can have homeomorphisms to Rn. So, chi1 taking us to V1, chi2 taking us to V2 and so on. And essentially what this tells us is that for every point P, which is an abstract element of this abstract topological manifold, there corresponds a point in Rn. Point in Rn means what? x1, x2, xn, n numbers. So, essentially you have a coordinate associated with every point on the topological manifold. Now, yesterday I did not have time to talk about what about this intersecting regions which get mapped to this intersecting region. So, this point for example P, let us say you have P, which of course belongs to the entire topology, it belongs to the topological manifold, but in particular P belongs to the intersection of U1, U2. And hence, the object P will have one set of coordinates because it is mapped to the open set V1, another set of coordinates because it is also mapped by chi2 to this point. In other words, consider this following mapping, because P is mapped into, let us call this point let us say is x1, x2, xn, because it is a point in Rn. This point will have the following n real numbers describing this point, but this same point, because it is also mapped by chi2, will have the same point, will have the coordinates y1, y2, yn. Obviously, there is a relation between the yi's and the xi's. What are the relation? It is very simple, because the chi1 inverse acting to this point gives P. So, chi1 inverse of this point takes me back to that point P, and chi2 acting on point P composition. So, chi2, the composition of 2 mapping, this acting will give me y1, y2, yn. Is a composition of 2 functions. We remember the set theoretic definition of composition. If I have 2 functions f of x and g of x, g of another, I mean any real number y, then g composition f of x is defined to be g. First you act f on x, you will get a real number, and then g acting on f of x. This is a definition of composition of 2 functions. So, chi2 composition chi1 inverse, which will act on this set of n real numbers, will take it to y1, y2, another set of real number. So, it is a real function taking n real numbers to another n real numbers. Okay. These two charts, remember these are two charts. What are the charts? This is a chart u1 chi1 and this is a chart u2 chi2, and u1 and u2 has an intersection, and because of that the point P belongs to both the charts. u1 chi1 and u2 chi2, these two charts are said to be differentially related if this function is infinitely differentiable. Remember, this is a function of n variables taking to another n variables, and we know what we mean by smooth function. If infinite number of partial derivatives with respect to x1, x2 up to xn are well defined, then such a function is infinitely differentiable, and therefore, when such a thing happens, if this is, as mathematicians will say, if this is a C infinity function, meaning infinitely differentiable, then we say that these two charts are differentiably related. Okay. All right. Because the transition function, this chi2 chi1 inverse, the transition function is infinitely differentiable. That means it's extremely smooth. When that happens, then the chart u1 chi1, u2 chi2, which have common intersection, they are said to be differentiably related. Now, remember, what's an atlas? Atlas is collection of all the charts that cover the entire manifold M.
Yeah. So definition includes the other part as well, where you take chi.
Oh yeah, of course, correct. So therefore, the other way around, that is y1, y2, yn can also be written as chi1 composition chi2 inverse of. So yeah, so both ways when they are infinite. They are both C infinity differentiable, but the functions are inverse of each other. So this is a function, call it f of x1, x2, xn going to y1, y2. The other is f inverse, which will take y1, y2, yn to x1, x2, xn, and both should be infinitely differentiable. So then we say that the two charts are differentially related. If in the entire atlas for all such regions, because there are common regions, for all such non-empty intersecting sets, if the charts are differentially related to each other, then such an atlas is called differentiable atlas. Okay? I am not writing it down because intuitively we know what we are stating. We are saying that all such collection of charts which are differentially related, then such an atlas will be called a differentiable atlas. Now, if your topological manifold has a complete differentiable atlas, such a differentiable manifold is called, such a topological manifold is called a differentiable manifold. So, in other words, because from now onwards we will be talking about differentiable manifold, differentiable manifold is a topological manifold with a complete differentiable atlas. All right. Right. So now I'll go over to the other sector. I'll have to erase all the past writings. So here is past, here is future. So now past will be erased. Right. So we will, from now on, we will only be associated with differentiable manifold. Now let's talk about a smooth function from one differentiable manifold to another differentiable manifold. So consider a function f which is mapping from manifold M to, we'll be now talking about differential manifold. So mapping from one differential manifold M to another differential manifold N is a continuous function, and we are asking the question, when will we call this function as a smooth function? Smooth in the sense of C infinity, but then mathematicians relax it to Ck, means k times you can take the partial derivatives, but those are more details. We will stick to C infinity differentiability. Right. So this continuous function f, when is it called C infinity differentiable function? Again, remember, because these are differentiable manifold, then we can talk about what happens to the charts. Remember, in this manifold, let's say there's a chart on the open set U and the homeomorphism chi to Rn, okay. This under F will go to a open set V belonging to the differentiable manifold N, and what should we call the homeomorphism in N? Let's say psi. So remember, what is chi? Chi is a homeomorphism from U to Rn, while psi is a homeomorphism from V to the dimension of the n dimensional differential manifold may be different. So it could be, let's say, R L. Okay. So this is can be mapped using chi to Rn. By mean, there are several such chi's depending upon charts, and this by several collection of psi is mapped to R L or some. Yeah. Okay. So therefore, chi inverse of that coordinate x1, x2 up to xn will take me back to the point in M, and this point M, when f acts on it, it takes me to that. So f composition this. So this will take me back to N, but then psi acting on that will take me to RL. So this object, this function takes a point in Rn to a point in RL. So those coordinates, let's say, are some z or P1, P2. This is RL, so PL. Now this is a function of n variables taking us to L real numbers. If this function is infinitely differentiable, so if this function, is infinitely differentiable, that means C infinity differentiable, then f is smooth, or C infinity smooth, is a smooth function. By the way, I mean this should happen for every chart, not just for a single chart. Okay. By the way, this is a general function from any differentiable manifold to any other differentiable manifold. Of course, because the dimensionality can be different, this function is not a bijective function in general. So, we have got a general notion of a smooth function. Now, let us come back to the smooth curves. We were talking about curves, and now we will specialize on smooth curves, because after all we have defined what is a general smooth function. So, smooth curves so as we yesterday we briefly mentioned, you have a differentiable manifold M and you have the real line R, and you take the interval AB and a mapping from this interval, let us call this mapping C of lambda. Lambda belongs to AB, so lambda belongs to the interval AB, and C of lambda is here. So, there is a image of the interval AB in the differentiable manifold. This is the image, and I mean say you can this is, let us say, C of A, this is C of B, and in general this could be the point P could be C of lambda 0, let us say, okay, lambda 0. And because we have defined the general smooth function, I will also impose that this C lambda function is also smooth. So that we are now talking about smooth curves in the manifold. Of course, there are through point P, note that through point P there are infinite number of curves. You can have infinite number of such functions. So, through point B, so if this is C1, this could be C2 of lambda, C3 of lambda, and so on. And at every point there will be a tangent to the curves. But remember, these curves, these are in abstract m dimensional manifold. We do not know what is their representation, but tangents themselves are abstract. But that is the reason why we have already talked about homeomorphism to Rn. We can ask, what is their image in Rn? What does a curve, this abstract curve in this differentiable manifold, how does it look like in Rn? And that is the whole reason why all these machineries of topology, topological manifold, homeomorphism, all these were set up. Just like in quantum mechanics, your Hilbert space with state vectors ket psi, they are completely abstract. Only when you take a basis like position basis or momentum basis, the inner product of basis elements with kets, you get the wave functions, which are complex numbers, which are much more real, because you can write them down in terms of two real numbers. But abstract ket psi, you do not know how you can express them in terms of numbers. So, I am sure, I do not know whether the mathematicians already know it, whether L. E. Cartan was inspired by what was happening in quantum theory. So, perhaps that is why he developed this differential geometry, so that you have an abstract notion of vectors, dual vectors and so on. Right. Now, we intuitively know that because you have these abstract curves in the differentiable manifold, smooth curves, we have a notion of tangent, but how do they look like? So, now we have to therefore go back to their homeomorphic image in Rn. So, again I have to erase this part of the boat. Okay. So, let us draw a bigger picture of the differentiable manifold M, and you have this curve going through a point P, and let us say this point P belongs to a chart U of chi. There can be other charts also, but it is okay. And this is my point P, which is C of lambda 0, and this curve has been obtained by a mapping from the interval A and B on the real number line. This curve, because of chi, which is a homeomorphism to Rn, is mapped to another curve, and these are now, these points on the curve are x1 lambda, x2 lambda, any point. I mean, yeah, at this point of course this is lambda 0, xn lambda 0. And all the points in Rn, it is also a smooth curve, everything is smooth, everything is differentiable. So, this is the image of that abstract curve in the Rn space. Okay. But in the Rn space, I know what is a tangent vector. The tangent here, I know what the tangent vector here. The tangent here, this tangent, this vector, how do I call it? Remember, this is associated with point P. Let me call it V of P and the ith components, I lambda. One of the components. So, what is Vp ith component at lambda 0? This is nothing but the dxi by d lambda at lambda 0. Okay. There is something, you think of 2 dimension or 3 dimension and you know that this is correct. Okay. So, in the Rn, I know what the components are, but now I want to know, well, what does this correspond that, I mean, what is the tangent vector here for which that is a realization, that is the representation in Rn, that is the question we are asking. And this is where a complete leap of imagination happens. So, as you know, in any new way of looking at it, things will not logically follow. You have to have a leap of imagination, and that is what is the hallmark of true creativity. Okay? Because we do not want, I mean, notion of vectors and all that, yes, it is associated with the tangent to the curve, but we do not want the vector to be tied up strictly with a curve. So, there is something else has to happen. So, that was the leap of imagination, and Carter, I do not know how to rightly pronounce Cartan, probably Cartan, what he realized is that vector somehow has to be an operator on functions. Now, where did he get this idea of the vector being an operator on functions? It is from the fact that we have a notion of directional derivative of a function. Remember that in normal R3, after all electrodynamics or fluid dynamics, we often do it. Supposing you have your three-dimensional space, this is your three-dimensional space x, y, z, and you have flows taking place, and you have a function. So, these are the flows, the vectors dr by dt, dr1 by dt, dr2 by dt. There are these different velocity flows happening, and there is a function, some f of r is a function, and we ask ourselves that when you are moving through the flow, how does f change? Okay. We all know the answer. The answer is that if you want to go for one of the velocities dri by dt along this, how does f change? What is the expression? How does it change? Along that means how does the f function change along the flow? This is nothing but dot gradient of f of r at that point, wherever point P is there. These are all taken at point P. Okay. So, therefore, this vector, by the way, this vector is not really related to f, but nevertheless this vector is inducing a change in f through an operator. Okay. All that clear? And Cartan was inspired by that. He realized that a vector must be an object which acts on a function. Okay. And that was the whole idea, to define what is a vector. Now, we will give the definition of vector in differential geometry. Okay. So, now what I will do is I will first draw a picture here and then erase this. Now, you have a notion of a function on real line. So, you have the real line, and you now have functions. This was the curve C. So, I will call the function, real valued function, as f. So, what is f? F is the mapping from the manifold, differentiable manifold M to R. Okay. So, what does f do? F takes a point P belonging to the manifold and maps it to the real number R. But your chart, okay, so take this object. If P belongs to this chart, then chi inverse acting on the coordinates x1, I will suppress lambda 0, I am talking about lambda 0 because we are talking about point P, but it will be involving too much of writing. I will just call it x1, x2, etc., xn. This will give me the abstract point P, and f will act on it. F will act on it and produce one real number. Okay. Okay. This is one real number, and we can ask what is, so this is now what is d by d lambda of this? Remember, this is a real number at point P, but point P could have varied, the lambda could have varied, and we are asking what is d by d lambda of this number. how does f change when you move along this path? Remember, f is a mapping from M to R, and we are asking how does f change when you go along this curve, and it will change. Okay. So, this clearly, because this is now a function of x1, x2, xn, and therefore, this will be okay, let me write it down, then I will explain. So, this is dxi by d lambda. This I know how it is happening. Okay. Okay. Dot, I'll say something and then we will see what we mean. Dot, now is that I'll have to have a nomenclature. Let me call it V. V of so I have written several things, I have to explain, and summation over I to n. Remember, go back. What is this object? This object is nothing but dxi by dt del by del xi of f summation over I, right. Okay. Okay. Because why I can do that? Because f composition chi inverse is a function of x1, x2, xn, and it is a real number. This is a real number. This is the tangent vector in the Rn space. Vpi, I do not know what Vpi is. Vpi is something which has n indices I that acts on f. Okay. And this object, so this provides me a mapping which says, and this is a real number. So, this says Vp is a vector at point P associated with the curve C, which is a mapping, okay, it is a mapping from x1, x2, xn, that means Rn, I mean n tuples, to a real number. Okay. So, this when it acts on f, which is a function of this, f meaning f comma chi inverse, it goes to R. This is the abstract definition of the vector at point P. So, in other words, vector acts on this object and produces one single number. Okay. So, in other words, V of P, chi is after all chart dependent. In other words, it should happen for all charts. So, V acts on the function f, and after acting, what is it? Is a real number. So, this is of real number. So, now we have a notion of what is the tangent vector here, because this is the component of the tangent vector in Rn. So, in the abstract way, this object V is the tangent vector in the manifold, and what it does is associate, and V is abstract tangent vector associated with curve at point P, which when it acts on the function f, it takes a real number, it maps it to a real number. So, if you read Meisner-Wheeler-Thorn's book, it will say it is a machine which takes the function and regurgitates one real number. That is what a vector at point P is, and you can do it at different points. So, you can have a vector field After all, what is a field? Field is a quantity that you can define on different points on the manifold. But at this point, it is this which it is doing there. Okay. Now, there are certain properties we must elucidate regarding the vectors. So, I will probably have to erase that part of the board. By the way, I didn't write completely, so here I should complete the expression. I have written symbolically at VPI, but what is this object? There is nothing but I equal to 1 to n. Later on, we will assume there is an Einstein summation symbol. We do not have to write the sigma because I and I are repeating. So, we will assume that whenever we have repeating indices, we already mean that there is a summation, but in the beginning we have to be careful to see what is happening. So, this object is nothing but dxi by d lambda. What is VPI? Is nothing but simply del f by del xi. That is what this is. Go back to this, your 3-dimensional thing. It is just nothing but this. That means, how does the real number to which f is mapped as you move along the curve, how does it change? So, therefore, partial derivative with respect to this xi's. In other words, this complicated object Vp can be thought of as dxi by d lambda multiplied by the partial derivative dl xi. So, this essentially tells me that the Vp vector is equivalent to, oh, these are all at point P, by the way, these are all at point P. This Vp vector is equivalent to dxi by d lambda at point P times del by del xi. In the coordinate basis, that means we are talking about the Rn coordinate system. So, therefore, when we talk about basis, you will realize what I mean. So, in the coordinate basis, Vp is equal to this, but you need not have chosen coordinate basis, okay? Then it is abstract quantity. All right. And note that Vp by itself is independent of the function f. F has disappeared because this is a linear thing acting on f. You give me any function, I just have to put p and I will get a real number. So, therefore, the vector is operating on the function and producing a real number. F by itself has disappeared from the scenario, although we needed the f to see what does a tangent vector in the abstract manifold, what is it doing to f. But after doing all this, we know you give me an f, I will tell you what Vp does to that f. But at the back of the mind, you know that it is associated with a curve. Okay. If you change the curve, the tangent vector also changes. Okay. Right. So, now we have established this, we can immediately ascertain certain properties. First property is Vp is a linear operator. That means, first property Vp acting on f plus g is simply Vp acting on f plus Vp acting on g. This is obvious because del by del xi is a linear operator. So, I do not have to show this. Similarly, the other one is also obvious. It is a Vp acting on any real number alpha times the function f is alpha Vp f. So, that means this is like a linear operator, but there is something else which linear operators in linear algebra or linear vector spaces do not share. What is it? That Vp acting on composition of two functions is f composition Vp acting on G plus Vp how does it follow? Because if you, this is also obvious, I will not work it out detail, but it's so obvious, because when it acts on f composition C, del by del xi will act on f composition C, but del by del xi satisfy Leibniz rule. Derivatives of product of two function is function times the derivative of that function plus derivative of that function times the second function. So it's obvious, and therefore this rule is also satisfied by the vector at point P. This is the so called Leibniz rule. I forget, yeah, probably Leibniz rule. I don't know whether the spelling is correct. And Leibniz rules always tell you about an operator which is like a derivative operator. Derivative operators always satisfy the Leibniz rule. Normal linear operators which we learn in our undergraduate days and on linear vector spaces, there is no notion of their acting on product of two vectors. So that difference is here. Now, see, when the way it has been written down, because if you try to put in, the notations will become horribly complicated. So that's why mathematicians don't put it. But remember, it is associated with a smooth curve. So you can have another vector field at point P if your curve is different, and there are infinity of such curves. Okay. So there will be a vector associated with each curve. Then you can ask, if you add two such vectors, will it be a vector? Okay. What is the answer? The answer is yes, this will be a vector. What ensures it? This is ensured by this. If you had another curve, then, so this is the image. To this point there will be another curve, there will be have x bar I, let us say, and lambda prime. But for the other curve, you can parameterize by the same lambda. The tangent vectors will now be dx bar I by d lambda. If you add the two vectors, del by del xi is same. So you will take common and this will get added. And it is a regular tangent vector in Rn, and because these forms a vector space in Rn, so therefore your VPs also form a vector space. Therefore, indeed at point P you have a vector space which is the collection of all such VP, because each VP is associated with a curve at that point, and there are infinite number of curves, so therefore there are infinite number of vectors, and the collection of all VPs which are equivalent to d xi by d lambda del by del xi at point P, and different curves will have different tangent vectors in the Rn. So collection of all such forms a vector space. And it is called TPM, that is associated with the manifold, and the vector space corresponds to one single point, and this is called the tangent space. So because of TPM, it is designated this called a tangent space at P. It is called a tangent space at P. Pictorially, yesterday I talked about pictorial thing. You can think of S2. If you take the surface of the sphere S2, take any point, then the plane tangent to that will all the vectors passing through this and so on. That plane contains all the vectors tangent to this point. It constitutes, if S2 is your manifold, then this plane is the TPM. Okay. I mean, at another point, there will be another tangent. So, and with this picture, it is clear that the tangent space does not belong to the manifold. It is a tangent space which is just touching the S2 at one point. The collection of all such tangent space is called tangent bundle. I mean, it generalizes to fiber bundle, and they are very beautiful stuff, but we will not talk about them. Okay. Obviously, if you have a vector space, you can ask, any vector space will have basis. So, a general basis of a vector space, basis of TPM. So, basis is a collection of vectors, and it is n dimensional. Why it is n dimensional? There are n components. So, it is a n dimensional vector space, form say, and the dimension of TPM is n. That is obvious because there are n tuples. Okay. So, you can choose any abstract thing. Let us call the basis EA, A going from 1, 2, 3 up to n. This is a basis. Any vector, any VP, any vector VP can be expressed as a linear combination of EA. So, therefore, there will be VA times EA. And I will assume that Einstein summation convention is being followed, because A is repeating, it is being summed from 1 to n. The vector Vp itself is an abstract operator. EAs are the abstract operator, while VA, they are the components. VA belong to Rn. So, VA, so this belongs to, this entire thing belongs to TPM, while VAs belong to Rn. And now I will make a correspondence with tensor calculus. So, in tensor calculus, VA is what? A contravariant vector. So, VA is a contravariant vector, because the indices are up, contravariant vector. I will erase this part. And people talk about orthonormal bases and all that. If you have a notion of inner product, you can have basis. Okay. So, we will talk about all that soon, but before I talk about the inner product, we will first talk about what happens when you have a coordinate transformation. First of all, there is a natural basis. Abstract basis is that EA vector. There is a natural basis. Natural basis is this. It is called the coordinate basis. Okay. The so called coordinate basis of the tangent space TPM is this set del by del x I going from 1 to n. So, there are n such elements of the basis del x1, del x2 and so on. Okay. And any therefore, any vector field we have already written. So, therefore, Vp any vector can be written as dxi by d lambda del by del x. That is how we began. I is being summed over, and this is called the coordinate basis. That is a natural basis, and in this course we will only use the coordinate basis. Okay. But there are interesting things can be done when you are in the abstract realm, talking in terms of abstract basis. Then there are a lot of interesting things that happen. But for our short course, we will stick to the coordinate basis del by del x1, del by del x2 and so on. Right. Okay. Now we ask the question, well, this is with one coordinate system. If your charts change, then the same point gets mapped to another set of coordinates. What will happen then? So, that we know from our differential calculus, when the coordinates change del by del xi in a different coordinate, different mapping, if you go from, if this point, the same point is now mapped to x prime 1, x prime 2, earlier it was x1, x2, then we know that del by del x prime I by partial derivative rule, chain rule of partial derivative goes to, so this goes to del x prime I, which through partial chain rule in partial which is known in partial derivative is simply del by del xi, j, I is already there. So, a new dummy index j is being summed over. And but the vector Vp does not change. That's the new thing. Those who are only familiar with tensor calculus and not differential geometry. In the differential geometry, under a coordinate transformation, the vector itself does not change. Vector is Vp, it is an operator. Its components change. Why? Because the same Vp can be now written as the same Vp. It will not change. It will now be written in terms of del x prime j, del x prime j, now j is being summed over, okay. D, not j, because the curve is same, dx prime d lambda. And we know del by del x prime is this. So, how is it related? So, same Vp now, is this as well as this, but this tells me how the components themselves are changing. So, therefore, this thing the same as del x prime j by d lambda, del by del x prime j is nothing but this, which is del x L by del x prime j del by del x L. Now, I am making a correspondence with tensor calculus, that the traditional way we learn general relativity, that is when we do not use differential geometry, we think of vectors in terms of tensor calculus and how the components transform. Now you see from this relation, so Vp is this, Vp is also this. That tells me how dxi by d lambda transforms. That means dxi by d lambda is equal to this, because remember, so this is I, if I had called this L, after all the dummy index, okay, then dxl by d lambda is simply this. So in other words, we have derived that dxl by d lambda is simply equal to del xl by del x prime j into dx prime j by d lambda. And as you can see, in the traditional learning of GR tensor calculus, how does dxl by d lambda therefore transform? It transforms like a contravariant vector. But in the differential geometry language, the vector does not transform, vector is still Vp. That is something which becomes counterintuitive when we first are exposed to differential geometry, because, and it happened to me when I started learning GR, I learnt it in the traditional tensor calculus approach. But then when later on I was exposed to differential geometry, I was told that vector itself does not change, it is an arrow, it does not change. That was counterintuitive. Then slowly, I had to go through all this rigmarole to finally understand what the differential geometers are saying. This is a standard way of learning. So this is a contravariant vector, because this is how contravariant vectors transform. Are there any questions? Because this is the point. I am making a connection with differential geometry with tensor calculus. After some time, I will only use tensor calculus, because there are many things we have to go fast, and we will use only tensor calculus. But I am making a correspondence between differential calculus, differential geometry and tensor calculus here. If there is any doubt, please ask me.
Okay, the set of all tangent vectors Vp that forms a vector space. So if I am not wrong, is the underlying field is R?
Yes, the field is R, we are not complex numbers. Unlike in the case of quantum mechanics, the state vectors, the Hilbert space we use in quantum mechanics, the field is C. Yeah, good. Yeah. So that's one big difference.
Okay, so I think the conditions 1 and 2 are sufficient to call it as a vector space.
Yeah. No. This is about their being linear on the functions f, linear operators. But here it does not tell you how to add two vectors. Addition of two vectors comes when we try to add the components and see that if you have two different curves, one tangent in the image in Rn will be this, another tangent will be dy by d lambda, dxi by d lambda plus dy by d lambda is also a tangent vector, which is because it is d by d lambda of xi plus yi, and therefore it forms a vector space.
Yeah, that is a closure property.
Closure property. Correct. All right. Yeah.
There is an online question.
Yes.
What will determine the dimension of the tangent space?
Yeah. So good question. So tangent space is completely determined by the dimensionality of the Euclidean Rn space where we are talking about, because the tangent in this curve, the image of the abstract curve in the Rn, the tangent to that curve has the same dimensionality as n. So therefore, dimension of TPM is also n, where the manifold is homeomorphically mapped to Rn. So manifold dimension is also n. Any other question? Because now I am going to cotangent.
TPM does not belong to the manifold.
TPM, no, it is a separate vector space. It is a linear vector space, while the manifold, I mean, we have not even talked about how to add 2 points.
Is it a subspace of
No, it is completely a different space, because remember, it is determined by the curves that are going through M. So, each vector in TPM is an abstract tangent vector to the abstract curve passing to the point P. So, it is all abstract. Only thing we know is what happens when it acts on a function f. Good. So, now we have established what is a tangent space at point P, and collect, and there are infinite number of points P in the manifold, and for every point there is a tangent space. The collection of all this tangent space is termed as tangent bundle. Now, another structure we will define. That is how mathematicians say that how many different interesting structures can be defined with our space. Now, we will talk about cotangent bundle. Okay. So, now which part? I will erase this part. So, note something, I mean, important part to stress is the tangent vectors in the tangent space, they do not change under coordinate transformation, they do not even know what is happening in the, when you do different charts, they live, they have their own independent existence. When you talk about the components in terms of n real numbers, then you talk about transformation of the components. Cotangent space or is a dual space, or is also called the dual of TPM, and it is termed as T star. All right. So, this is a linear vector space which acts on TPM and produces a real number. So, now you can see that the mathematicians' obsession with mappings, okay, they are obsessed with talking about different mappings. Of course, that is a purpose, but when you go through mathematical analysis, initially you get bewildered with so many mappings one is talking about. Okay. So, if I will vectors I have called with an arrow, Vp with an arrow. So, the elements of cotangent space I will use this tilde. Okay. If this belongs to the cotangent space Tp star. So, first of all, yeah, then is a mapping from TPM to the set of real numbers, because we are, as pointed out, we are using the field, real number field. So, our dual space is a mapping from TPM to R. In other words, what does it do? You give me a vector. So, this will act on a vector. Oh, by the way, I should mention P. So, these are all local quantity. We are all talking about P, because yeah, when this acts on Vp, it produces a real number. So, this belongs to the real number. Now, we can talk about orthonormal basis and so on, because this will tell me it takes one vector, produces a real number. So, this in a way tells me how to have a notion of inner product, okay. And therefore, the basis, so orthonormal basis both for TPM and, so I will call it orthonormal basis of TPM and the dual space T star M. Okay. So, just like EA are the basis abstract basis vectors. So, now I am going to consider orthonormal basis both for TPM as well as T star M. So, let EA be a basis orthonormal EA, and remember it is a set A going from 1 to n and another set. By the way, now I will not talk about P, but remember we are all talking about at a given point P. So, I will suppress the index, I mean that P thing, and EB, again A is going from 1 to n, B is going from 1 to n, and EB let be the orthonormal basis so basis in plural, because there are two sets of orthonormal basis of TPM and TP star M respectively. Okay. If they are the orthonormal basis, a choice of, I mean after all you can choose your own orthonormal basis, then the condition is that E tilde B when it acts on E vector A, you get the Kronecker delta A P. That is the definition of orthonormal basis. Oh, these are so far abstract, but abstract thing is fine, they have their own aesthetic beauty, but we have to I mean we have to talk about concrete thing. One of the things we have already a concrete basis in vector space TPM we have already talked about, namely del by del xi. So, therefore, you ask, before that I must have yeah, I should have mentioned about one thing. Yeah, that is required, otherwise we will not make much of headway. Yeah. Okay. So, one of the things I can tell you is that one particular kind of element of the dual space, cotangent space, is something which is denoted as d of f. If f, what is f? F is a smooth function from the manifold M to the real number, and we will talk about this later on. What is this d tilde of f? Now, d tilde of f is one of the elements of TPM, and the action, by the way, yeah, I should here I have to ponder what should come, what is the sequence, correct sequence. First do that or do this, but perhaps it is important to do this. So, we will tell what is this d tilde acting on f, the so called exterior derivative. We will come to that, there is still time. Yeah, but this is an element of the dual space. Take it from me, I mean at the moment I am not explaining this symbol, and the notion of, and because this acting on Vp is becoming like this, is a real number, and the idea is that df, when it acts on one of the basis vectors, let us say del xi, because remember this, when it acts on a vector, produces a real number, and del by del xi is a valid vector. What is that real number? It is this, del f by del xi. So, for given a function f from the manifold to the real number, d tilde of f is an element of the dual space. It is called, by the way, I should have used this. This WP tilde are called one forms. So, yeah. So, are called the one forms. Truly speaking, I should have called it, I take it as a joke, I should have called them hectors. If we call this as vectors, those should be called hectors. I mean, this is those who have read Greek mythology, Homer's Iliad, remember the fight between one brave warrior, Hector from Troy, and Achilles. So, if Achilles is vector, then one form is a hector. This is just a aside, and there is a reason, because I want to give a pictorial representation of vectors and hectors or one forms. Yeah. So, this is sometimes also written, this action is also sometimes written as this. Probably Eli Cartan was inspired by the Dirac bracket in quantum mechanics. So, d of f acting on del by del xi is also written as this, and when this happens, you just get del f by del xi. Okay. Then you can immediately identify, if you have the coordinate basis of vectors, del by del xi, I going from 1 to 10, and you can immediately identify what are the coordinate basis one forms. Using this rule, because you can see that after all d of xj, remember they are mapping from TPM to real numbers. So, they act on del by del xi, the vectors. So, it is, we are now talking about one particular choice of basis, and this is same as this notation bracket d of xj del by del xi, and using that rule, this is simply d of xj, or rather del of xj. The d is not del by del. So, del xj by del xi, but what is del xj by del xi? Because if xj's are independent coordinates, then del xj by del xi will be Kronecker delta. So, this is delta ji, because they are functionally independent. They are exactly equal to 1 only when j is equal to 1, with the same coordinate, but otherwise different coordinates are functionally independent of each other, and therefore, partial derivative del xj by del xi is this. So, therefore, indeed, using this we know that this and this mutually form orthonormal basis vectors. Okay. So, Meissner, Wheeler, Thorne, they use the following pictures, because physicists would always like to use pictures. So, vectors are the arrows, and what are the one forms? Because one forms, when one forms act on vectors, you get a number. So, for them, if this is a vector v, one form df are represented by surfaces of f equal to constant. because d of f. So, these are f different constant, f equal to different constants, and this is your d of f. So, you can think of Hector encountering vector producing a real number. What is the real number? Del f by del xi. Or if it's an arbitrary vector, it's a, you have to suitably, so, okay. So, let us talk about arbitrary vectors. So, if, I should have mentioned that also, yeah. So, d of f, it's a linear, I should have mentioned some of the properties. This is a linear action. So, some of the properties I should have mentioned. So, WP, this is a condition, it's a mapping, but it's a linear mapping. So, V plus U will be WP of V plus WP of U. Similarly, scalar multiple, if you put lambda Vp, then WP acting on lambda Vp, lambda will come out WP. So, because of that, df acting on a general vector, if you take a general vector, now I am not writing the subscript p. We know that everything is happening at one point on the manifold. This is understood. So, you can ask if df acting on del x mu is this, what is this? So, this by definition is d of f comma v can be, you can write it in terms of the basis vectors del by del xi. So, this is nothing but vi del by del xi, and it is already linear. We have already talked about the linear properties of this mapping, and hence using the linearity, this becomes vi will come out, and d of f, remember I is being summed over. So, it is a summation del by del xi, and this is nothing but vi del by del xi of f. So, df acting on v gives you in the coordinate basis vi, which is the contravariant components of the vector v, times del by del xi of f, and you can easily verify this is invariant under coordinate transformation. Here there was no reference to coordinates, but here there are reference to coordinates, but we know how vi transforms a contravariant vector, and del by del xi transforms as covariant vector, and therefore, you have a result which does not depend upon coordinate system. Okay. So, you are again back to your old calculus. This is indeed a inner product. So, before there are so many things to say, I must not jump the gun. So, this is like an inner product, but note one thing, metric has not entered. So far, metric has not even made a cameo appearance in the whole theory. We are talking about differential geometry, but is there a notion of metric? So far, no metric, and yet we have a notion of invariant inner product. That probably was also another motive of Cartan. He wanted to find out how far can he extend without talking about the metric, which is so important for general relativity. How far can you go? So, up till this point, metric G mu nu has not yet come in, okay. And yet we have a notion of coordinate independent quantity, that means invariant under coordinate transformation, object which is independent of coordinate system. Okay. Now, so we have to Prakash had said I can take some extra time, right? Yeah. So, we have a notion of components, contravariant components of a vector. Okay, Vi is you can ask what are the components of a one form, arbitrary one form. So, let me erase this part. By the way, the elements of differential geometry can be used not only in general relativity. Those who want to know its diverse application, read Bernard Schutz. I had given the reference, Bernard Schutz's geometric methods in physics. He uses this in thermodynamics. He gives the example, and Bhashwati probably has already begun how to use differential geometry to write down Maxwell's equation in a very compact notation, even more compact than the 4 vector notation, which is del by del x mu of f mu nu equal to j mu. There are still a lot of symbols here, but in differential geometry the symbols get minimized. So you can ask, okay, great. We have talked about components of a vector when you choose coordinate basis del xi. What about component of a one form? So let us consider the one form. D of f. What are its components? In the basis. I have no space for the question mark, so question mark I will put here. When you write, how Indologists discovered that Harappan script, we don't yet decipher, we haven't deciphered the Harappan script, the oldest civilization in India. There's alas he is no more, there's a very famous Indologist, Airavatan Mahadevan. He realized that Indus Valley people, wrote from right to left, unlike the way we write Devanagari or Tamil, we write from left to right. How? Because many of the Indus Valley symbols, they got cramped as it went to the left mode. Just like I didn't have space for the question mark, it got cramped. So that's how Airavatan Mahadevan sort of deduced that Indus Valley people wrote from right to left. Okay. Yeah. So what are its components? Very easy. Take d of f. This can be always written as del f by del xi, d of xi, I being summed over, they are repeating. So therefore the components are del f by del xi. Components of df therefore transform like what? Covariant vectors. Components of vectors transform like contravariant vectors. Components of one form go by this. By the way, I didn't say, after all, D is not an ordinary differential. Why is this true? That's because, after all, this action is already defined, right? Where is it? Yeah. This action is already defined. So, therefore, let us see whether this happens. The answer is yes. So, D of f with del by del x j, this if you take, we know what is it? This is nothing but del f by del x j. And so is this, because this object dxi, when you take it with del xj, again this bracket is a linear bracket. I should have mentioned, but I didn't, but this is a linear both in the right argument, also the left argument. So this can go out. So del f by del xi dxi by del xj, and this is the Kronecker delta we have already seen, which is del f by del xi. Remember, whenever indices are repeating, they are being summed over. Del f by del xi, this Kronecker delta, delta ij, because this forms a orthonormal basis. I have written it there, and the same as del f by del xj. So, on one hand this is this, so therefore, this must be true. I have just proved that this must be true, and hence the component of this one form are del f by del x, partial derivative of del f by del xi. Okay. So, in other words, what is the summary of all these elaborate exercise? The components of a vector transforms like a contravariant vector. The components of a one form transforms like a covariant vector, but neither the one form nor the vector change when there is a coordinate transformation. They do not change. Okay. For a different curve, the vector will be different. For a different function f, the one form will be different, but otherwise under coordinate transformation they do not change. Now, I come to the notion of D. This D, but before that I must talk about something else. The space of all one forms is termed as omega 1 at the point P. We are always talking about, so the set of all one forms. I mean, this we have already said at P the set of all form T P star, but because we are going to talk about higher forms, the space of one form which is identical to T star P m, the space of all one form are is designated is also omega 1 at the point P. I will not mention, perhaps I will put P here. The reason is that there will be higher forms we will talk about. So, space of two form, what is the two form? I have not yet talked about. Space of two forms will be omega 2 P, while functions, normal functions from manifold to real numbers, those are called omega 0. They are 0 forms. So, what are 0 forms? 0 forms are the functions, Functions mean they are the smooth functions going from manifold to R. So, at the back of the mind there is a manifold, all these are happening, they are acting on the manifold, but they themselves do not belong to the manifold. Other functions and this space is designated at omega 0. Now, I will erase that part of the board. Yeah, now I will talk about wedge product. No, first before that I have to talk about direct tensor product before I go to wedge product. So, tensor products. Of vectors and one forms. So, first let us take tensor product of vectors. So, if you have, so I am going to suppress the P subscript because everything is happening at a point and you can do it for any point. So, if you have a vector V and another vector U, you have a notion of tensor product. So, what is this? This belongs to the tensor product of TPM cross TPM. So, someone will say, I mean, yeah, you have defined this symbol, but what does it mean? Its meaning is, what do they do when they act on functions? Remember, what do the vectors do? Vectors, when they act on functions, they produce numbers. Okay. So, therefore, you say, what does it do? So, when V, U act on a pair of functions, let us say f and g, what you get is V of f, which is a real number, multiplied by u of g. That is what they do. That is what is a tensor product. Okay. And you can have the whole set of, you can have arbitrary tensor products. And as you can very well imagine, so take it as a tutorial, arbitrary tensor products, when you write down their components, there will be contravariant tensor. So, this, their components of V tensor product U, their components will be what? V I into U j. So, it is a particular case of a second rank contravariant tensor. But then you can add, your tensor product is this, you can add to it another tensor product and so on, then you can generate arbitrary second rank contravariant tensors. So, these are tutorial, I am not giving, you have to play around with it to prove that when you take the components, they are contravariant tensors, and you can create arbitrary rank contravariant tensor by taking suitable direct product and some linear combinations of these tensor products of vectors and adding it to another tensor product of vectors. Okay. But they are so trivial that I do not want to spend too much of time on this. Similarly, you can take tensor products of one form. So, you take W1 one form, similarly take tensor product of another alpha as another one form. Okay. So, this is a tensor product and it belongs to T star PM tensor product TPM, and this tensor product T star I will, so in standard language we have defined omega 0, omega 1, this will be omega 2 point P. Okay. No, not yet, no, this is incorrect. That is why the omega notation, otherwise people would not have, differential geometry would not have defined omega. No, that is not correct. We will talk about what is omega, this is not, it is different from that. So, again tensor product of two one form, again you have to say what does it do? After all, what does tensor form do? It acts on vectors. So, one form acts on vectors. So, therefore, alpha, when it acts on two vectors u, v, then this is nothing but w acting on u multiplied by, w acting on is a real number, multiplied by alpha acting on v. Order is maintained, that means this is first written, the second, this first, so this will act on this will act on the other. And by the way, by now we have introduced several notation, this is also, the notation is also same as w comma u, so that is same as alpha comma v. These are different notations actually. Okay. In particular, this is the problem. We run out of blackboard space. We don't have tensor product of blackboard spaces. Yeah, so in particular, let's consider tensor product of, let's say, d of f, d of g, and ask what does it do. So if it acts on del by del xi and del by del xj, then you get simply, which is same as df del by del xi multiplied by, because this will act on this will act on this, dg which is same as del f by del xi del g del xg. All right. So you know you can produce higher order tensor products, and then you can mix them, tensor product of one form vectors, and so that you can have mixed, their components will be mixed tensors. As you can see that their components, this is nothing but components, right? So this is a covariant tensor, second rank tensor. So you can generate arbitrary tensors by a suitable mixtures of tensor products of one forms and vectors. Okay, so you can have a tensor product. So far I talked about tensor product of vectors with vectors, tensor product of one form with one form, but you can mix them and produce this, use the same definition, and the components, when you suitably contract it with the basis vectors, you can generate arbitrary tensor fields. Okay. So that makes a connection with the tensor calculus and the differential geometry. Can I take 5 more minutes? I will just take 5 more minutes and introduce a concept, namely the wedge product. So far I talked about tensor product. Today I will stop by introducing wedge product, okay, so that tomorrow we talk about something that many of the tutorial problems that Bhaswati has formulated, they can be answered, namely two forms and all that. So far we are dealing with only one form. Now comes a notion of a wedge product. Wedge product, what it does, it creates product of one form which is antisymmetric. Okay. So therefore, you take d of f is one form, and there is a notion of d of g. Now we must tell what the wedge product on basis vectors are first. Okay. So yeah. By the way, these are the calculational tools, wedge product, exterior derivative. Those are mechanical calculation tools. You must do a lot of tutorial problems, and it is this that helps in mathematical calculations in general relativity. You do not need to know this entire motivation, understanding all that. Very many people, they use the exterior derivative, wedge product just as rules, and they can calculate things. And probably you are already using tutorials. Apratim's tutorials will also have this, using software, how to do this algebraic computations. So the wedge product of two basis vector one forms, so take dxi and dxj. this by definition is an object which is antisymmetric. This is same as minus dxj wedge product dx. In other words, what is this? This is antisymmetrized tensor product. This is nothing but d of xi tensor product d of xj minus d of xj tensor product d of xi. So, at the basic level, it has come, it is constructed using the notion of tensor product. Okay. This is the definition. The wedge product is a definition. Now, you can ask, well, this is the using the you have told me if you have two basis vectors belonging to the basis of the one form, how to create another strange quantity, namely dxi wedge dxj. But what is the usefulness? What does it give me? It gives me another mathematical quantity called two forms. Any general two form beta, let us say. So, beta is a two form. Any general two form can be written as beta mu nu or beta ij. At the moment, I am not using mu nu. When I talk about metric and our space time manifold, then I will use the usual mu nu. At the moment, I am using ij because we are talking about Rn, which is a Euclidean space. It is not a Minkowski space. So, I will use ij for the time being, and you will have dxi wedge product dxj. By wedge product, you know it is ultimately antisymmetrized tensor product, that we must realize. Okay. But because of the antisymmetry, you can immediately realize it is only the antisymmetric components of beta ij that will contribute. The symmetric part will not contribute, okay, because this. So, what does this say? If I and j are equal, what is it? Is 0. If I and j are same, it is 0 because dxi wedge dxj is minus dxj dxi. So, if I and j you set equal, anything which is negative the other thing must be identically 0. So, therefore, an arbitrary two form by definition is this, is such its components, because we have chosen the basis, its components form say second rank antisymmetric tensor. Okay. Is that clear? So, now we are making a correspondence with second rank covariant antisymmetric tensors with some beasts called two forms. What is the standard or rather more common antisymmetric second rank covariant tensor we know of in physics? Is the electromagnetic field tensor, because we know F mu nu by definition is del by del x mu of. Now, I came back to mu nu because we are talking about Minkowskian space time. By very definition, this is antisymmetric because F mu nu is minus F nu mu. Okay. All right. Now, a very interesting thing will happen. Can I, so far whatever I have said, can we write using this notion of d tilde and wedge product something for the electromagnetic case? So, I will probably stop. I am still I have crossed just the last thing before we stop. Okay. Now, suppose I say I define a one form A as A mu dx mu. Dx mu is a one form. In our language, any one form somewhere, I was using I and j, but now I am using mu nu, remembering that earlier I and j were going from 1 to n, but now I am talking about Minkowski manifold, mu is going from 0, 1, 2, 3. So, this is a one form by definition. Now, you ask, can I have something which will take from me to this? F mu nu, remember F mu nu is a second rank tensor, and I have already told you for every second rank tensor there is a 2 form. So, you ask, suppose I write F tilde as F mu nu dx nu wedge dx nu. So, then this F tilde is a 2 form. Okay. But then you ask, well, how is this related to this? Can I go from here? Is there a relation between this one form and this 2 form? And you will say that, well, there is a relation, because after all F mu nu is related to this. There comes the notion of exterior derivative. So, I will just stop by introducing the exterior derivative. Exterior derivative d is an operation that maps, remember this is a 2 form, the set of all 2 forms is omega 2, just like set of all functions is omega 0, set of all on one form, set of 2 forms, set of space or set of all 2 forms is designated as omega 2. So, exterior derivative is an operation that maps omega k to omega k plus 1. That means, it takes an element from kth form and maps it to k plus 1 form. Example, d acting on 0 space of function d of f belongs to omega 0, but this belongs to omega 1. Similarly, we want that d, when it acts on one form, it takes to 2 form. That means, d of a one form A belongs to the 2 form omega 2. And this is precisely what it does. The exterior derivative action is so defined that d of A is nothing but, so d of A is nothing but the 2 form F12. Okay. And this immediately tells me how does d act on A. Okay. We will do it in our next class, but now the stage is set. You can do the tutorial problems. So, it turns out that the 2 form beta, like 2 form beta, when d of A acts on the one form, this object we will show by telling what the property of the exterior derivative. Okay. D of A is so defined that d acting on A will produce the components are this. I will stop here, and tomorrow we will take up the nitty-gritty, but I think from now on we can, that is all right. Okay. We can start the tutorial problems on at least the homogeneous Maxwell's equation. For the inhomogeneous, we have to, tomorrow I will introduce the hot star dual operation. Yeah, okay, great, thanks, Bashud. All these operations, you have to do many problems so that you get familiar with the calculational tools. The calculation tools are mechanical, but you have to do a lot of exercise to become more conversant. while I concentrated on the fundamental aspects as to why these calculation tools to begin with were invented by Elie Cartan.